This is a presentation of the 19th Annual Colorado Snow and Avalanche Workshop, a program of the Colorado Avalanche Information Center, Friends of CAIC, and the National Avalanche Center, presented by Dinafit and Pomoka.
Hi, I'm Bex, an avalanche forecaster at the Colorado Avalanche Information Center. Today I'd like to present a project Ron Seaman-Hoyce and I have been working on this summer. For geographical reference, our primary forecast responsibilities are for highway corridors in Colorado. Avalanche workers have long applied weather thresholds as predictors of avalanche release to plan mitigation missions. Timing these interventions is a source of stress for forecasters. We like to keep the roads open and the traffic flowing. However, when you consider the consequence of an avalanche to the roadway, putting lives or infrastructure at risk, compared with a $1 million estimated economic loss for a 1-hour closure on Interstate 70, the pressure feels very real. Consequently, at the CIC and many other forecast operations, one of the biggest challenges of forecasting for these spatially distant areas is timing mitigation missions and closures for optimum effectiveness. What else are some other operational benefits of using threshold values? Setting these values enhances communication with coworkers and stakeholders. As I stated before, they improve timing and help us to schedule missions for peak instability. This helps forecasters to focus on critical values during periods of high psychological pressure. Typically, these values are set during periods of relative calm and can be adjusted as the storm progresses. Also, knowing when the paths are reaching critical thresholds, we can allocate resources on multi-pass mitigation days. They also help forecasters plan fieldwork and snowpack observations. The definition of a threshold is the magnitude that must be exceeded for a certain result to occur. Forecasters derive their threshold values based on snowpack conditions and forecasted weather parameters. When threshold values are reached, the action is taken. As you're aware, there is either a plethora of data or it is very sparse, so having threshold values helps to filter out the noise and maintain focus during busy storm periods. During these large storm cycles, we don't have the ability to travel to all of our areas at the same time. Any number of challenges exist to hamper travel, including the number of avalanche paths, distance between avalanche areas, and traffic density. This was made painfully clear to forecasters on the I-70 corridor during January of 2017, when they became viral sensations after multiple areas became active at the same time. We were also all blessed to relive this experience in the big storm of March 2019. Following these events, we debriefed and brainstormed areas for improvement. We focused on 3 key points: improving communication, improving threshold accuracy, and developing an alert system. As usual, Ron took the ball and ran with it. He began looking for a way to alleviate the midnight forecaster panic. He developed a threshold alert system that texts forecasters when remote telemetry reaches a predetermined threshold. This helped increase awareness of changing weather conditions across the forecast area. To establish thresholds, he sifted through the 153,000 or so avalanche records we have in our database and chose the relevant avalanches with robust recording. Weather data and avalanche days were collated from the nearby wind and snow tower sites. He then compared the weather leading to avalanche mitigation missions, where avalanches hit the road and when they stopped in the track. He used these different weather parameters to establish recommended operational thresholds for himself. Here's an example of precipitation data breakdown for the Seven Sisters group for 6, 12, 24, and 48 hours before mitigation. Using these results, he chose to set his threshold at the lower end of the 80% confidence interval. This process was repeated for wind data. The model uses a simple method of assessing single weather parameters, like recent snowfall or winds, but it doesn't use a sophisticated approach to combine parameters like precip, wind, and temp occurring concurrently. During long drives between passes, we had time to think and wondered if there was a way to tailor our weather forecast page to display past, present, and future forecasts for individual avalanche paths, indicating when they may reach critical concurrent thresholds set by a forecaster. If we could correlate forecaster knowledge with avalanche occurrence data, we could help forecasters learn their areas of responsibility and fine-tune their experientially learned rules of thumb. This is a representation of our fantasy forecast page. Most forecasters we queried found the CIC's display of current conditions in the WRF forecast model easy to use. So blending these two resources would allow forecasters to view past specific data at a glance. The red boxes are forecast to determine thresholds for wind, temperature, and snowfall. When we see all relevant boxes overlap in the forecast, we could delve deeper into the timing of operational recommendations. The red line separates the weather station observations, so the past and current weather conditions, and from the weather forecast. So this is why we call it our fantasy forecast page. During our conversations, Ron suggested I start to learn a programming language so we could have the computers do the work for us. This smelled a little bit like a trap to me, but I went along with it. And I turned up at our next meeting with my proudly displaying my first program. And Ron showed up with 64 pages of this. Nevertheless, he stuck with me and we continued to investigate data indicated thresholds. To help identify critical weather thresholds, we rely on anecdotal forecaster experience. Taking this information, we then began experimenting with more data-driven thresholds. We wanted to identify weather stations that showed correlations between weather parameters and avalanche activity to the roadway. We chose the Seven Sister avalanche paths located on US Highway 6 Loveland Pass as our test area. These paths have a high return period and are one of our longest running data sets. After defining our test area, we identified weather stations used by forecasters for avalanche predictors. In this case, wind, temperature, and relative humidity was taken from the Seven Sisters weather station. Snowfall and change in SWE were taken from the Loveland Basin SNOTIL. We looked at 122 avalanches that listed road or non-road hits from the CIC database. Here we are using violin plots to display our data. The reason we use these plots is because they present the difference in a population's distribution better than box plots. These populations do not look very different on the box plot graph to the left. However, the difference in the populations is clear when you're looking at the violin graph on the right. The red indicates wind speeds resulting in avalanches to the highway. The blue shows that when wind speeds are too fast or too slow, they are not effective for wind loading. Here, we compared wind speeds and direction that led to road-hitting avalanches in red and non-road hitting avalanches in blue. As you can see from the chart, there is some weak correlation. To help identify relationships inferred from the last slide, we applied projection to wind direction and speed variables. You can see here in the bottom left corner a strong indication that 3-hour winds from the west-northwest play a part in avalanches to the roadway in the Seven Sisters. We all know that forecasting for avalanches is complex, even when ignoring the characteristics of the snowpack. We quickly realized we needed a way to look for multi-dimensional weather variables. When you start to combine 2 and 3 weather parameters, such as temp, wind, and snowfall, you have a lot more multi-dimensional combinations to explore. We identified machine learning as a more effective tool to examine weather combinations that correlate with avalanches to the roadway. Some examples of relationships we hoped we could show include wind playing a greater role in avalanche activity when it's snowing, and effects of changes in temperature during snowfall. We used a few methods like principal component analysis and multiplying variables to reduce our multi-dimensional problem into a one-dimensional problem. In this animation, we're looking for the line that projects the best X and Y axis relationships, correlating with the most avalanches to the roadway. By now, we were running over 12,000 different parameters. This proved to be a few more parameters than we could work through in a day, so we used a machine learning model to identify the most important parameters for our system to highlight. Specifically, we trained several algorithms of decision tree forests on the data and asked the models which combinations of parameters have the most effective predictive power. This slide demonstrates the basic idea of decision trees and decision forests. These violin plots are comparing the results from 2 single parameters on the right and the orange ellipse, compared to 4 multi-dimensional parameters on the left. The blue represents avalanches that stopped in the track, we called non-road hits, and the red represents avalanches that made it to the road. When looking at the means, indicated by the yellow arrows. You can see if we use single variables as predictors of avalanche activity to the road, the means are the same or close. When you compare this to the multi-dimensional plots, you see the spread between the means, demonstrating that multi-dimensional analysis captures a lot more avalanches to the roadway. In other words, when we combine the data in the 4 violin plots on the left, we end up with a more powerful discriminator between the times when avalanches reach the road and the times that they don't. And here are some initial value results. The algorithm highlighted a strong indication of avalanches to the road in the following conditions. If snow is falling up to the time that we shoot, and the maximum PI is 0.15 SWE in the 12-hour interval prior to the shooting, accompanied by average wind speeds of 17 miles per hour. As you can see, it's far more detailed than we would probably use operationally. Interestingly, an experiential forecaster knowledge stated that when air temperatures are above 20 F, higher SWE values are needed for avalanches to hit the road. And this model also highlighted that relationship. We are still in the preliminary stages of investigating the predictive power of data-driven thresholds, but have been encouraged by our results so far. In conclusion, obviously, there is a lot going on when it comes to weather and avalanches. Machine learning can simplify a multi-dimensional problem by selecting weather parameters that predict avalanches to the road, and our initial results show promise for helping with operational forecasting. We'd like to thank all the CAC staff for putting up with our constant requests for opinions and data. Thank you.